Suppose, let me go back to Schrodinger equation now. Okay, I want to prove something here. I want to define one more physical quantity that we haven't discussed earlier. Okay, one more physical quantity, and I want to prove some equations here. Okay, let me go to Schrodinger time dependent equation. I h bar dou psi by dou t is equal to h bar square by 2m, like that, is it? Now look at here, I will go for 3-dimensional equation, then I will generalize that one to, then I will take special case as 1 dimension. Okay, I'll go for 3-dimensional equation. So minus h bar square by 2m. I hope you know about Laplacian, am I right? Del square psi, that psi should be big psi, okay? But let me write it as psi itself, okay? Psi plus v of psi, okay? Let me take it like this. I hope you know what is del square, okay? In case of 3 dimension, del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square, okay? Look at this one. Whatever we do, this is a property of Schrodinger equation itself, okay? So this is Schrodinger time dependent equations where psi should be written as, look at here, it's a 3 dimension. Psi should be written as x, y, z, comma t, or psi should be written as r, comma t. In this case, okay, that I haven't mentioned. Now what I do is I'll take complex conjugate of the whole equation. V is a real potential, okay? V is real. V can be time dependent also. I have taken most general situation, okay? But V is real. So when I take article complex conjugate of the equation, minus I h bar dou psi star by dou t is equal to minus h bar square by 2m del square of psi star plus v into psi star. Am I right or not? Is that okay? Now what I do here is I am going to multiply this equation with psi star, this equation with psi, and I'll subtract. Okay, I'll multiply above equation with psi star, I'll multiply this equation with psi, and I'm going to subtract. Then what will happen here? I h bar psi star dou psi by dou t, am I right? Psi star multiplied and subtracted. I'll take one step directly. So when you subtract, what will happen is minus minus plus psi multiplied dou psi star by dou t. This is the left hand side, okay? In the right hand side, when you multiply by psi star here, when you multiply by psi here, when you subtract, it will be 0. So again, v cap is v itself, okay? V cap is v itself. That's why you can take psi anywhere here, okay? In this expression, you can take psi anywhere. But in this expression, you have to multiply with psi like this, isn't it? You have to put a bracket and then you have to multiply, isn't it? In this expression, that whatever the multiplication, it should be outside this derivative, okay? But here you can keep it anywhere. When you subtract, it will go, okay? I hope we did similar steps somewhere, isn't it? Earlier. So this is equal to, look at here, minus h bar square by 2m psi star del square psi minus psi del square psi star. Is that okay? Now what I can write here, look at here. So dou by dou t of, can I write psi star into psi? This whole thing. Is that okay? And I'll take this h bar, I'll get cancelled, one of the h bar. I'll take this I into denominator here. What will happen is minus h bar by 2im psi star del square psi minus psi del square psi star. Is that okay? Now here comes one vector calculus theorem actually, okay? We will look into that one in electrodynamics part, because I am dealing with 3 dimensions, it's a Laplacian, am I right? Here comes one vector calculus theorem, that is minus h bar by, so 2im del dot, okay, divergence of one quantity, that is psi star, that is psi star del psi, gradient of psi, okay, minus psi gradient of psi star in bracket. Psi star del psi minus psi del psi star. That's how we read, but it is a gradient. I hope you know something about vector calculus, gradient of a scalar, or just leave it again, later you will understand, okay, in case of electrodynamics. You can look back into this equation again, okay. So that means if you do this one, you will get this one, okay. I don't have a direct proof here. I don't have direct, intermediate step here, but when you do this one, you will get this one. When you do this one, there are two terms which comes here, two terms comes here, total 4 term comes here. Among them 2 term will get cancelled, only 2 term will remain actually, okay. Is that okay? Now, what we have proved here is, look at here, what I do here is, I'll take this h bar by 2im along with this one. Is that okay? So shall I rewrite here itself? Minus del dot h bar by 2im. Can I write like this? This one dou by dou t of mod psi square. Now I am going to rewrite this equation. I am going to define this whole quantity as j, okay, and I am going to rewrite the equation. The equation is like this. So dou, what is this one? Can I write as rho mod psi square, probability density, by dou t is equal to minus del dot j. You can take divergence. It's a divergence of a vector quantity. Am I right? So j of r comma t. Because wave function is a function of r comma t. Remember, I was talking about 3 dimension. Okay. Now, along with this wave function, along this with again this rho of r comma t is what we call probability density. Am I right? Probability density, isn't it? Now we have one more quantity, j, vector quantity, okay, which is equal to h bar by 2im psi star del psi minus psi del psi star. It's a gradient. We call this known as probability current density. It is always real. This is always real, am I right? This is also always real.
I think this equation from continuity equation.
This equation is continuity equation. We need to look into this equation now. Now look at here. What does this this is famous continuity equation. This comes in fluid dynamics. This comes in electrodynamics. In many cases it will come. In case of electrodynamics, this will be your charge density. This will be your current, electron current usually. Okay, current due to charges. But here it is probability density. We call this as probability current density. Because again, we are just copying the electrodynamics kind of idea, isn't it? Current density, you can see, isn't it? In case of our electrodynamics, it is current density. It's a charge current density. We can say like that, isn't it? So this was charge density actually. Okay. Now what does it say? Okay. Now look at here. So if at this rho is a point variable, isn't it? Rho density is a point variable. You can talk about density at some point, isn't it? It's a point variable, okay? So now, at some point in space, okay, if probability density is decreasing with respect to time, okay? We have one more negative sign here, okay? Let me take this is positive. Then this derivative will be negative, isn't it? Speak out.
Okay.
So time derivative is negative means it is decreasing with respect to time, isn't it? Suppose at some point in space, if probability density is decreasing with respect to time, so that means, so some current density exists, divergence of current density exists. Divergence of a vector field means it will talk about how much that vector field is going outward from that point. These are all point operations we shall see in electrodynamics, okay? So that means divergence is non-zero means, okay? So that means this vector field is diverging from the point. Is that okay? So that means J is diverging from that point means, so you have some region, okay? In that region, rho is decreasing with respect to time. So that means this J, vector field J have this kind of nature. It is diverging from that point. Is that okay? Because it's a divergence of J, am I right? This divergence exists means the vector field is going outward from the point actually. Speak out.
So sir, this probability, current density, I mean, we are taking with only R part.
No, again we are fixing R. We are fixing R. So again, so take R naught actually. Is that okay? So take one point in space, okay? And you can take derivative at that point, am I right? Divergence at that point in space, isn't it? So this is a time derivative, this is a space derivative actually, okay? Again, you can vary time, you can keep time as variable, is that okay? You are taking time derivative of this one, you are taking space derivative, why not? It's a function of two variable, R as well as T. Now what I am saying is, so this is non-zero means, okay, this is diverging from the point. Okay, are you getting my point?
Yes.
Now if this is diverging means this should be decreasing. Rho should be decreasing with respect to time. So that is the meaning of this continuity equation. Now we shall try to analyze this equation. I mean, we shall try to understand this equation. Look at here. At some point in space, okay, at some point in space, if suppose rho is decreasing, what do you mean by that? Probability density is decreasing, isn't it? Probability of finding the particle is decreasing, isn't it?
Yes.
So rho is decreasing with respect to time means probability of finding the particle is decreasing. So that means particle is trying to go outward from that region. Then only that probability will decrease, isn't it? Or there should be some flow of particle outward from that region. Not spread, flow of particle in the spatial point. I am not talking about x-axis, y-axis. I am talking spatial point. Particle is trying to go out from that region. If probability density is decreasing means particles are going outward from that region of interest, region of that spatial region. Is that okay? So that will lead to divergence of current density. So that is the meaning for the, that will give the meaning for this one. That means this will talk about flow of the particle. This will talk about flow of the particle. Can I say roughly like that? Probability current density, it will talk about flow of the particle. And if there is flow of particle outward from the region of interest, then there exists divergence of this J. Okay? If particles are flowing outward from the region, so J will talk about flow of the particle. Okay? Flow of the particle. Just like again our current density, am I right? Our electron current density, it will talk about flow of electron. Isn't it? Just compare it with what you call electrodynamics idea. So similar to that one, it will talk about flow of particle here. Wait a second, let me complete my argument. So now, so what will happen is, so these are equivalent statement, am I right? This is equal to this one. If there exists a flow of particle outward from the region, if this is non-zero, then probability density at that point will decrease. If particles are going outward, probability of finding the particle is decreasing at that spatial point. Or If probability of finding the particle is decreasing, that means particles are going outward. It's a kind of conservation law. Is that okay? It's a kind of conservation law. Again, it's a charge conservation law in case of electrodynamics. Okay, from charge conservation law, you can prove this one. So here it's a kind of particle conservation. You can say like that. Is that okay? No, we are not doing position measurement here. So here again, here I am not talking about measurement. Here I am talking about some inbuilt phenomena that is happening. Okay, I am not taking it again. This is a result of Schrodinger equation. Am I right? What does Schrodinger equation say? That's what I am trying to say. Okay, at time t naught, you are just finding the probability density. At time t greater than t naught, again you are finding the probability density. If suppose that probability density is decreasing with respect to time, that means some flow of particle is there from the outside of that region.
Okay.
That is the meaning. Yeah. So that is the meaning of this continuity equation. So that's why it will talk about flow of the particle. Probability current density is always a real quantity. It will talk about flow of the particle. Is that okay? Pick out. Again, you will understand little more in electrodynamics, okay, after getting the idea of divergence and all, okay. If divergence of J exists, that means rho will be decreasing with respect to time. Okay, that is the basic.
So here probability current density means only the flow of particle, not anything else.
Yeah, for probability current density, it will talk about flow of particle. I better to say like that, because you can't give the same interpretation as in case of electrodynamics, isn't it? Flow of electron per time, like that. You can say flow of particle per time. Actually, you can give that kind of idea. Flow of particle per time, just like in case of what you call electrodynamics. Okay, you can give similar definition here. But here we are talking about particles, not charges. Okay, this is not charge density. This is probability density. Okay. Suppose at some region of space, if suppose probability density is increasing with respect to time. Okay, so then there will be what you call incoming beam of particle. There should be incoming beam of particle. Then divergence should be negative. So that negative positive, the derivative will be, time derivative will be positive if rho is an increasing function. Speak out. It's all about derivative, whether it is negative or positive. Am I right? Derivative is negative means decreasing function of time. Derivative positive means increasing function of time. Isn't it? Yeah. No. Again, in case of stationary state, there will be no flow of particle. Okay. So these again, we will see what kind of wave function this J will be 0, J will be non-zero. Is that okay? So again, I talked only about decreasing rho. Okay. Try to think about increasing rho with respect to time. Suppose in some region, if rho is increasing with respect to time, that means particles should be flown into that region. If particle flown into that region, your divergence of J will be negative. Del dot J, it will be negative. Negative, one more negative, positive, that says what you call probability density is increasing. Time derivative is positive. Is that okay? That is the meaning. Now we shall see this quantity. J vector is equal to h bar by 2im psi star del psi minus psi del psi star. Okay. After electrodynamics, do some three-dimensional problem. Now we shall restrict ourselves to one-dimensional problem. Okay. Now look at here. So J is equal to h bar by 2im. Okay. So this is 3D. So this is 1D. Okay. So psi star dou psi by dou x, okay, minus psi dou psi star by dou x, okay, in case of one dimension. Okay. Now look at here, let me take two examples here. Example 1. Let me take wave function Okay, again you can take time independent or time dependent. Okay, if you even if you take I think time dependent wave function, what will happen in case of stationary state, this psi star into psi will come. Okay, time part will come one side, it will go actually. Okay, so let me take our what you call free particle state. Okay, psi of x is equal to a e power I kx, where k is real, remember. Or you can take kx minus omega t. Suppose if you need time dependent wave function, you can take kx minus omega t also. Okay, but let me take this one because that e power I omega t, that part will not affect, isn't it? Because you have psi star into psi, but derivative is with respect to x. Time part will come one side. Okay, I hope you got that idea. Is that okay? Now find probability current density for this state. Is that okay? Yeah, speak out.
Sir, your imaginary parts are included, but in case of probability current density are here.
Yeah, wait a second. We shall see. We shall see. That's a good question. We shall see what would happen. J is equal to h bar by 2im psi star a star e power minus ikx into dou psi by dou x. That means ik into a e power ikx minus psi a e power ikx. Psi star derivative means minus ik would come, a star e power minus ikx. Check this out. What is this one? Ik minus of minus plus ik, isn't it? 2ik mod a square h bar by 2im mod a square into 2I into k. Just check this out. Now look at here, I got cancelled, 2 got cancelled, h bar k by m into mod a square, real. So this is always real quantity. No need to worry about this one. You have I, again maybe it may be complex. No. Look at here. Suppose if I is not getting cancelled, then what would happen? You will see here. I'll take example 2. So psi of x is equal to, suppose our bound state of what you can take. Let me take it like e power minus some kappa x. Suppose x is greater than 0. In case of our Dirac function value, am I right? One side. Let me take only one side of it. Okay. Let me find current density at some positive x value. Okay. Now do the calculation where kappa is real again. Okay. Quickly do the calculation. A star e power minus kappa x into minus kappa e power minus kappa x a star into a mod a square. Let me write mod a square here, minus again mod a square, so e power minus kappa x, again minus kappa e power minus kappa x. Am I right or not? Minus kappa, minus plus kappa, these two will get cancelled, you will get 0. Look at here. In this one, as you said, there is no I term which came out, isn't it? Isn't it? If suppose this exists, this would be imaginary, isn't it? Look at here, it got cancelled. This is equal to 0. If our function is a real function, this may be complex, okay? This can be either real or complex. If our function is a real function, okay, functionality part, if that is pure real function, our probability current density will be 0. You can remember this point. Is that okay? Or even you can see this expression itself, okay? If psi is real, okay, I mean, if our function part is real, we can always take that normalization constant or multiplicative constant also, we can take it real, isn't it? That's our choice actually, multiplicative factor, okay? So now if psi is real, you can see here itself, am I right? If psi is real, psi star is same as psi, isn't it? Then this should be 0. If psi is real, j equal to 0. That's the observation. Is that okay? So that's why this kind of function where this kappa is real, will not talk about any particle flow. Probability current density is 0. I told probability current density will talk about flow of the particle. Okay. The same thing will happen in any of your bound state, isn't it? Particle in a box, particle in a harmonic oscillator, or wave functions are real. Probability current density is 0. It will not talk about free flow of particle. Suppose particle in a box or particle in a harmonic oscillator. They are bound problems actually. Particle will not go to infinity in that case.
Sir.
Yes.
Sir, here a to the power I k h square k by m. This is velocity, right?
Yeah, you can say this is velocity into mod square. Yeah, so this is a velocity. If you take this as a free particle, h bar k is actually your momentum by m. Yeah, that's correct. Because so this j will have the dimension of velocity. You can remember that. If they ask any dimension. Yes. Yes, speak up. No, wait a second. Mod a square may also have some dimension. Okay, it will have dimension. Mod a square, no, it will not have dimension.
Mod square not.
No, it will not have dimension. It will have dimension of speed. J will have, yes, speak out.
Sir, if function have no any imaginary term, you can also say current density is 0.
Yeah, you can say like that. Suppose this term doesn't contain any imaginary part. This term has imaginary part. If suppose this term exists, the total will be imaginary. That cannot happen. That's why it is 0. You can argue like that.
So sir, for every real wave function, so the
Probability current density is 0. 0. Now look at into this one. What was this one? This was our free particle wave function. Am I right? Solution. Now, so this will here current density is non-zero means it will talk about a kind of flow of particle. Particle can flow freely to up to infinity. Am I right? You can say mod psi square is non-zero at infinity. Am I right? In this situation, non-normalizable solution. So particle can exist at infinity. Particle can escape to infinity. Isn't it? Speak out. Free particle. No boundary at all. Am I right? This was free particle solution.
If I will take some boundary, then it will not.
Then again, our wave function happened to be real. We have seen particle in a box, harmonic oscillator, and our Dirac function well, isn't it? We have seen. In all such cases, j equal to 0. Because it will not talk about particle which can freely flow to infinity. Our wave function was normalized. Our wave function was 0 at infinity. Isn't it?
But sir, for harmonic oscillator, it is spreading.
Spreading is there, but at infinity it is 0. Am I right? For harmonic oscillator, isn't it? And if you find j, it is 0 in that case also. Harmonic oscillator state is a bound state. We say them as bound state. It will not allow particle to escape to infinity. It will not allow particle to freely move. Is that okay? If particle is allowed to move to infinity, then only your current density exists in this situation.
sir,
Is that okay? If current density exists, means particle is freely moving. Flow of particle. This is not a flow of particle actually. Is that okay? This will not talk about flow of the particle. Any of our bound state problem, either particle in a box, harmonic oscillator, or Dirac function well. Okay? So those wave functions will give j equal to 0. You can just observe that one, isn't it? Real wave function. Yes, tell me. Is that okay? For any normalizable solution or any of our bound state problem, whatever we have discussed, there was no probability current density. For our free particle solution, there exists probability current density. Now compare. Physically compare. Now these are bound particles. These cannot go to infinity. Am I right? So, but this is a free particle. This can go to infinity. That means probability current density will talk about a free flow of particle up to infinity, isn't it? Yeah, you can say like that. Real wave function always represent bound state. You can say like that because, yeah, you can say like that because if wave function is not real, probability current density may happen. Is that again, if probability current density exists, then that's not a bound state. That's a particle flow. It can flow out. Okay. No, stationary state. Again, this again you are going out of the track here. So stationary state, we can talk about probability of finding the momentum. Okay, those are not momentum states. Stationary states, our bound states, they were not momentum states. They had inbuilt momentum uncertainty. Okay, suppose if you take e power minus ax square, or if you take sine n pi x by a, they are not what you call eigenstate of what you call momentum operator. Remember, they had inbuilt uncertainty of p, isn't it? Any of these state, whatever you take, they are not a definite momentum state, but this is definite momentum state. That's why the factor momentum came here. Might be.
Then sir, if it is definite momentum state, then the s cross k by m, it can be the eigenvalue of velocity, sir.
Yeah, you can say like that, but we don't talk about eigen velocity operator here because momentum is the most general term, isn't it?
Okay.
Is that okay, Kushal? Quickly reply. So whatever bound state we had, okay, those had inbuilt momentum uncertainty. They were not momentum eigenstate. If they were momentum eigenstate, momentum uncertainty would be 0, isn't it? Sigma p would be 0. Sigma p were non-zero, okay? But here sigma p is 0. It's a definite momentum state. Is that okay? Yeah, observe these things. So that's a very good observation, okay? So that's why in case of bound state, our probability current density is 0, or in case of any real wave function, our probability current density is 0. Okay, if our wave function is like this, our probability current density will be non-zero. Okay, they may design some other function also where j is non-zero. Okay, you should do that problem properly. But if they give again real part of functionality, you can quickly say j equal to 0. Whether a is real or complex, it doesn't matter. A star into a will come here, isn't it? You can see that. Okay. So now this probability current density is a physical quantity. It should be real, and it will talk about flow of particle, free flow of particle. Okay. Can I say like this? Yeah. Now one more thing you need to observe, okay? Suppose you are you have a potential, you have a potential, you have energy like this, okay? Energy E like this, okay? You have two regions here, okay? One is this region, other is this region. This is classically forbidden region, where our potential energy is higher than the energy, okay? This is classically allowed region, because your energy is higher than the potential energy, okay? Your kinetic energy is positive. In this region, kinetic energy is negative. We call this means classical turning point. I'll come to that point, okay? Speak out. Now look at here. In this region, let me try to solve Schrodinger equation. H bar square by 2m minus h bar square by 2m d square psi by dx square. Our potential is time independent, okay? I'm yeah.
What's the topic behind? Topic name?
No, so wait a second, I'll come to that topic. But observe the solutions of time independent Schrodinger equation. That's what I'm saying. Okay. So h bar square by 2m d square psi by dx square plus v psi is equal to e psi. Am I right? Just read out this one. D square psi by dx square plus two m e minus v of x by h bar square psi is equal to 0. Can you write like this? Suppose let me take v of x is constant for the time sake, okay? Because if v of x is variable, it will be what you call variable part would come. Am I right? Let me take it like this. Let me take it like this. V of x is constant here, but v of x is less than energy. V of x is greater than energy. Okay? Is that okay? Speak out. Now, I'm talking about this region, okay? Classically allowed region, okay? Where energy is greater than V of x, okay? And our kinetic energy is positive, okay? In this case, kinetic energy would be negative. Now, in this case, look at the solution, okay? So, E minus V is positive, d square psi by dx square plus I can write as k square psi is equal to 0, where k is equal to root of 2m E minus V divided by h bar. Now, in that case, your solution is, look at here, a e power I kx plus b e power minus I kx. In this situation, in the classically allowed region, when energy is greater than the potential energy, okay, when particle is free to move in any region, then there will be no what you call boundary or no what you call boundary condition, isn't it? Later, isn't it? Particle can free to move here. In that situation, look at here, your solution is like this. Observe that one, okay? And it will have some current density. This kind of solution have some current density. Observe that one, okay? So let me take this region. So this is this region. Let me take this region, okay? In this region, look at here. If I write this one, d square psi by dx square plus 2m e minus v by h bar square psi is equal to 0, okay? Now look at this one carefully. E minus v is negative here, am I right? E is less than v here. V is higher. So then what I do is d square psi by dx square. I'll take negative sign outside. I'll write 2m v minus e by h bar square psi is equal to 0, okay? I'm going to write like this. Then d square psi by dx square, I'm going to call it as kappa square psi is equal to 0, where kappa is equal to root of 2m v minus e divided by h bar. This is real. Why? V is higher. I am talking about this region. In this situation, look at your solution. In this situation, look at your solution. We have done, am I right? This situation came in case of our Dirac function value, isn't it? This situation came in case of particle, free particle. So a e power kappa x plus b e power minus kappa x. Both part will have current density 0. This part of the solution will have 0 current density. This part of the solution will have some current density. Observe this fact. That's it. Speak out. That means particle can escape here actually. Okay? Particle cannot escape here. I'll come to that point.
So, sir.
Yeah.
Sir, whenever energy is exceeding from the potential, then that part will not have the current density. We can say like this, sir.
No. Whenever energy exceeding potential, it may have current density.
Yeah, sir.
Yeah. But don't think that in case of harmonic oscillator, okay, energy is higher than the potential. It can escape. It can't escape. Okay, let me tell you. Okay, so that is my discussion. But I needed this observation. Okay, I needed this observation of the solution. Okay, so can I say like this? In case of classically forbidden region, okay, your solution is exponential. Can I say like this? So in case of classically allowed region, your solution is sinusoidal. Can I say like this? Because when you just split that one, it will be sin kx cos kx, isn't it? Just observe this fact so that next discussion would be quite easy.